Okay, hi everyone, and thanks for coming to my talk. Today I'll be talking about log rank and lifting for AND functions, and this is based off of joint work with Sasha, Shahar, and Weicheng, and my name's Sam. Okay, so the starting point for this talk is communication complexity, and I'll give like a simple setup for communication complexity that we're interested in here. So we start with a function f, big F, from two n-bit strings to a single bit. And we have two parties, Alice and Bob, and Alice has a string X, Bob has a string Y, and their goal is to compute F by communicating bits. So in particular, they're going to engage in some communication protocol pi. And what that means is Alice will send some message based off of her input. Bob will send some other message based off of the messages he's received so far, and so on until hopefully they compute the value of F, which is some value 0 or 1. Okay. And the notion of complexity that we're interested in for these protocols is the length, which means the number of bits, the total number of bits which are sent. And I'll use CC of big F to refer to this length of the shortest protocol pi computing this big F. Okay, so this is the way of viewing communication complexity from this protocol point of view. There's an alternative useful perspective, which is in terms of matrices. So here what we'll do is we'll view F, big F, as a 2 to the n by 2 to the n binary matrix MF. And we'll think of the protocol as acting on this matrix in a particular way. So this is the matrix. And what will happen is Alice will Alice will partition according to the protocol, and according to which inputs she would have sent 0 and which inputs she would have sent 1. Alice will partition the rows into two sets. Bob will do the same by refining the partition that Alice has already made, based off of the inputs on which he would send a particular message. And the result is that they end up partitioning the matrix MF into a small number of monochromatic rectangles. And what I mean by a rectangle is that it's a cross product of a subset of the rows and with the subset of a column, the subset of the columns. And by monochromatic, I mean that every entry in the rectangle is either 0 or 1. Okay, so with this perspective, it's not so hard to see that if we have a protocol if we have a low-cost communication protocol, so say we have a communication protocol for f of cost c, then this upper bounds the log of the rank of the matrix MF. So in particular, the rank is going to be at most 2 to the c. And this brings us to kind of our primary motivation for this paper, which is the log rank conjecture. And the log rank conjecture asks whether some type of converse to this is true. So whether it's the case that if I have a low rank matrix MF, binary matrix MF, if it implies the existence of a short protocol. And so quantitatively, this asks if the communication is going to be upper bounded by some polylog in the rank of MF. Okay, and so this is the question that we'd like to understand, and it is it was posed in the late 80s by Lovas and Sachs, and there's still relatively not too much known about it in the general case. So the best upper bound we know so far is due to Levitt in around 2014. And he showed that the communication complexity is upper bounded by roughly the square root of the rank. And the best lower bound we know of is something like quadratic, which is due to Goose, Patasi, and Watson. And in particular, there's some function which witnesses this quadratic separation, meaning if the log rank conjecture is true, then this constant up here will have to be at least 2. Okay. So what we're interested in studying then, given this kind of dearth of knowledge in the general case, is what about special cases? What if we place some types of restrictions on these matrices MF? Okay. So the types of special cases that we'll be interested in here are matrices which will be kind of the characteristic matrices of lifted functions. So a lifted function is defined in terms of 2 objects. The first is a function from a single n-bit string to a bit, and the second is a function g, which I'll refer to as the gadget. And for our purposes, we'll just think of the gadget as it'll take 2 bits and it will output a single bit. Okay, so the setup here is that Alice has n bits as input, Bob has y bits of input, and they'd like to compute f composed with g. And so the way we define f composed with g here is for each of these pairs, xi, yi, the ith input bit to f is going to be g of xi, yi. So this is kind of most easily understood in terms of this picture. So we have each of these separate copies of g. We can evaluate them, and then we want to evaluate f of those copies. Okay. So a couple examples. So first, we can say we can express the inner product mod 2 as a lifted function. So in particular, we can write the inner product as the sum mod 2 of these bitwise ands, and in this case, g would be the and of 2 bits. As a second example, we could write the equality of 2 strings as this and of the negation of these of the bitwise XORs. And in this case, g would be just the XOR of 2 bits. Okay, so why study functions that look like this? Well, there's kind of 2 advantages. The first is that there's a more streamlined way of designing communication protocols for functions of this form. And this is through by designing query algorithms for f. So what I mean by a query algorithm is something like a decision tree where it has an input x and it gets to ask some types of yes or no questions about that input. So a decision tree gets to ask for the value of particular bits, but we'll think about more general models where different types of questions can be asked. And query algorithms for f actually will give us communication protocols for f composed with g when we're using a query model that's related to g. So for example, and I'll make this more specific later, but for example, when g is the XOR function, the type of query model that will allow us to get communication protocols is so-called parity decision trees, which get to ask parity queries. So it can ask for the parity of an arbitrary subset of the bits. Okay, so this is the first advantage, is a simpler way of designing communication protocols. The second advantage is that the rank of the corresponding matrix is characterized by the sparsity of f as a polynomial in some basis that's related to g. So we write f as some polynomial, maybe in the Fourier basis, for example, and the sparsity is going to be the number of non-zero coefficients. So you might also think of this as the all-zero norm. And so this gives us a simpler way of understanding rank in terms of by thinking about it as a question about polynomials. So kind of using these 2 advantages, we can reframe the log rank conjecture. And this asks whether sparse functions have efficient protocols, since sparsity is now going to be equal to rank. And we also can relate these advantages to another setting called lifting, which I won't have time to talk about entirely, but we can think of it as the secondary motivation for this work. And lifting in this context asks whether low communication functions have efficient query algorithms. And so kind of coming to these two questions, this is going to be our motivation going forward, is trying to answer these two. And I'll note that we can answer both at the same time by designing efficient query algorithms for sparse Boolean functions. So the way we can see that is say the log rank, so say for log rank, so we have a sparse function. Suppose we designed an efficient query algorithm. Then by this first advantage that I've mentioned, we would then be able to get efficient protocols if the query algorithm is in the right model. And the lifting question, we can see because a low communication complexity function is going to correspond to a low rank matrix, and this will in turn correspond to a sparse Boolean function. And then if we can show that sparse Boolean functions have efficient query algorithms, then we're done. Okay, so in this lifted setting, we get this kind of streamlined way of answering both of these questions at the same time. And so that's what we're going to try to do. So I want to continue by kind of explaining a little bit about what's known regarding these questions. And I'll start by looking at XOR functions, which are functions obtained by letting F be arbitrary, but letting G be the XOR of 2 bits. So this first advantage of having efficient protocols following from efficient query algorithms can be framed formally here as saying that the communication complexity of F composed with XOR is upper bounded by twice the parity decision tree complexity. And here, the parity decision tree complexity, I alluded to this earlier. So first of all, we care about the depth of a decision tree. And this decision tree can ask queries of the form, so it can ask for the parity of an arbitrary subset of its bits. So this is what this first advantage looks like. This second advantage of this connection between rank and sparsity in this context can be framed as saying the rank of this matrix associated with F composed with this XOR gadget is going to be the sparsity of F in the Fourier basis. So what it would mean to design efficient query algorithms from sparse functions is to say that we have a Fourier sparse Boolean function and we want to design a short parity decision tree. Okay, so what's known on these two fronts, these lifting, the lifting front and the log rank front. So lifting actually is known. So we can show that we know how to show that the parity decision tree complexity of F is upper bounded by a polynomial and the communication complexity of F composed with XOR. And this is a result due to Hatami, Husseini, and Levitt. On the other hand, the log rank conjecture is unknown, aside for special cases where we restrict the F to have some special properties, like, for example, low F2 degree. Okay, so this is the kind of short summary of what's known for lifting and log rank in the XOR setting. And now I'll move on to AND functions, which is the focus of our work that's appearing in the conference. So AND functions are obtained by letting F be an arbitrary function and then picking G to be the AND of 2 bits. And trying to articulate this advantage, this query advantage formally, in the query model formally. So we're going to be concerned with a query model called AND decision trees, and AND decision trees will be able to ask for the AND of an arbitrary subset of bits. And the complexity measure that we care about is the depth of the AND of the shortest AND decision tree computing a function. And this first advantage becomes that the communication complexity of F composed with AND is bounded by twice the AND decision tree complexity. And the rank versus sparsity connection in this context says that the rank of f composed with and is equal to what I'll call spar of f. And spar of f is the sparsity of f in the monomial basis. And so I'll define formally what that means in a second if you aren't familiar. So these are what the two advantages look like. And so the question is, can we use the sparsity of f in the monomial basis to design short-end decision trees? And the main result of our work is that the answer is yes, up to a log n factor. So what we're able to show is for any choice of f, both the log rank conjecture holds up to this log n factor. So in particular, this communication complexity of f composed with and is upper bounded by a polylog in the sparsity times the single log n factor. And on the lifting side, we can show that the and decision tree complexity of f is upper bounded by a polynomial in the communication, again with the single log n factor. And prior to this work, there were a few results that worked for f with rather restricted combinatorial properties. So we view kind of a major innovation of this work as getting a result where we don't assume any structure about f except for the sparsity. Okay, and the way that we're going to prove this is kind of this two birds with one stone idea, where we're going to design short and decision trees for sparse Boolean functions. So let me now explain that in a bit more detail. So the setup I want to define sparsity in more detail for those unfamiliar with it. So the setup is that we have a function f from n bits to 1 bit, and we think of this as doing computation over the reals. And we'll represent f as a polynomial of this form. So we'll sum over all of the subsets of coordinates, and we'll have these monomials xs with coefficients alpha s. And the monomials in particular correspond to the product of all of the bits in the set S. And notice that this is equivalent to just the and of all of these bits. Okay, and so given the setup, the sparsity of f is going to just be defined as the number of sets for which the corresponding coefficient is non-zero, or the number of monomials for which the corresponding coefficient is non-zero. So two quick examples. The sparsity of and is just 1 because and is a monomial, and on n bits, or and on any number of bits. Whereas the sparsity of or on n bits is exponential, which you can just see by writing out or in this way, and then expanding it, expanding the product out. Okay, so this is the definition of sparsity, and what we want to do, and the way that we are going to design and decision trees for these types of functions, is by studying some type of combinatorial structure of sparse functions. So we'll look at this kind of question of structure, monomial structure of Boolean functions. So we want to think about the monomials as a set system, and we're going to study some combinatorial properties of this set system. And the set system that we're interested in is called, or the combinatorial property that we're interested in is just called, is the existence of small hitting sets. So a hitting set for f is just going to be a hitting set for all of the monomials of f. So in particular, it's going to be some set t, which intersects with every non-zero monomial. And I will mention that setting every bit in a hitting set to 0 makes f constant. And so this is just to get a bit of an intuition about the relationship between having hitting sets and restrictions for these functions f. And so what we can show is that first, that sparse Boolean functions have small hitting sets. And second, that if we have a sparse Boolean function with a small hitting set, then it also has a small and decision tree. Okay, so these are kind of the two main components of the proof. Two remarks. The first component, and we think of the first component as being kind of the most significant contribution here, technical contribution, is that this generalizes to small range Boolean functions. So it doesn't rely completely on being Boolean, it just relies on having a small range. So we can think of it as being any constant size, say. The second point is that the second bullet point, where we can design small and decision trees from this, from having a sparse Boolean function with a small hitting set, this is where we incur this log n loss. Okay, so I want to say just a few words about how we show this first part, which says that in more detail, it says that having a function f with sparsity r implies the existence of a hitting set of size polylog in R. And the way we do this is by introducing a new notion of like a variant of block sensitivity called monotone block sensitivity. And this will be sort of like a directed version of block sensitivity where we can only flip zeros to ones, but not ones to zeros. Okay, and the proof that sparsity implies small hitting sets can be thought of as happening in two parts. So the first part shows that sparse Boolean functions have low monotone block sensitivity. And this, was possibly implicitly kind of observed in a paper of Nissan Vigderson from the 90s. And this, but we frame it in some generality and show that, and this uses some tools from Boolean function analysis, specifically Nissan Segedi. The second lemma shows that if we have a sparse polynomial and it has low monotone block sensitivity, then there is a hitting set of size polylog, or of size polynomial factor in B times a log R factor. And this uses LP duality, and it requires a new random rounding argument. And this lemma 2 is, in our view, this is kind of the most technical part of the paper, and is the main technical contribution. Okay, so in summary, or so that's all I wanted to say about the proof. Is this usage of a new notion called monotone block sensitivity. In summary, what we show here is that we show this main structural result that sparse Boolean functions have small hitting sets of size polylog in the sparsity. And using the connections outlined earlier, we're able to show that this implies up to a log n factor, both log rank and lifting for and functions where there's no structural restrictions about f. So let me just conclude with a few open problems. So the most obvious open problem here is removing the log n factor. And this has to do with some more efficient way of designing and decision trees directly for sparse functions. So if you look at the paper, we actually need to go through a secondary notion of decision trees called a zero decision tree. And when we convert from a zero decision tree to an n decision tree is when we lose this log n factor. So if we could avoid this zero decision tree model, perhaps we'd be able to get rid of the log n factor. The second question I'll mention is about randomized versus deterministic and decision trees. So, so recall that randomized and deterministic decision trees, like standard decision trees, are equivalent up to a polynomial. For parity decision trees, there's a linear separation, but we don't know how this works for AND decision trees. What we do know is that we can show a log n separation, but we're interested to know if this is tight. So with that, I'll stop. And thanks to Alice and Bob, and thanks to all of my co-authors, and thanks for watching the talk.